Today we're going to start out looking at Chapter 7 on one sample inference. We're going to look at Section 7.1 on the basics of hypothesis testing. So there are two branches of inferential statistics. These are hypothesis testing, which we have not yet looked at, and confidence intervals, which we've actually already covered. Hypothesis testing is making a decision about parameters based on statistics and deciding, is a statement true or not, or is a statement likely true or not. Confidence intervals we use to estimate parameters based on statistics. So the question that we would ask with a confidence interval is, what is the value of a parameter, or what is a likely range of values? That is what we seek to answer by using confidence intervals. A hypothesis is just an educated guess about a parameter. The intuitive way to think about this is, let's find evidence to support our hypothesis. But the way this actually works is we assume that our idea isn't true. We gather evidence, and if that evidence would be very unlikely, assuming that our idea isn't true, then it's more likely that our idea is true. So we start with the assumption that our hypothesis is not true. This is called a proof by contradiction. What we do is we assume the opposite of our hypothesis is true, and we show that that can't be true. And if that happens, then your hypothesis must be true. All hypothesis tests go through the same process. Let's go through an example here. We're going to look at the life of an XJ35 battery. Let's suppose that the manufacturer of the XJ35 battery claims that the mean life of the battery is 500 days, with a standard deviation of 25 days. You're a buyer of this battery, and you think that this claim might be inflated. You would like to test this belief because without a good reason, you can't get out of your contract. Well, what do we do? First, we need to define what we are trying to measure. So we need to define the random variable. We're going to let X be the life of an XJ35 battery. We need to define the parameter. The parameter here is going to be the mean life of an XJ35 battery. This will be mu. I fixed this to add a mu. For our sample, we want to collect a sample, so we want to pick some batteries. You could ask the manufacturer to give you some batteries, but there's a chance that there could be some bias in the batteries that they pick. They might send you batteries that they know are going to have a longer battery life, for instance. So to reduce the chance of bias, it's best for us to take a random sample. And how large should this sample be? Well, the central limit theorem tells us that, well, at least 30 is probably a good starting size. So let's say we take a random sample, a simple random sample of 30 batteries, and we test their battery lives. And we collect the following data. So we have the battery lives for 30 of these XJ35 batteries. Looking at this data set, we can see that some of these battery lives are above 500 and some of these are below 500. But looking at all these numbers, we can't really look at these numbers individually to make a decision. So it might be helpful for us to calculate the mean. If we calculate the mean here, X bar is going to be 490. This is promising because this mean is lower than the manufacturer's claim, but this could just be a coincidence. The sample that we've taken may just happen to include a lot of short life batteries. So before we go further, it might be a good idea to formalize a few other definitions. We have what is called a null hypothesis. This is a historical value, claim, or product specification. This is denoted with H naught, or H sub 0. And an alternative hypothesis. This is the thing that you want to prove. This is what you want to accept as true when you reject the null hypothesis. There are two symbols that are commonly used for the alternative hypothesis, H sub A or H sub 1. We'll use H sub A, although you may see H sub 1. And sometimes this will be a capital A, sometimes it'll be a lowercase a. In general, these hypotheses look like this. H naught is that mu is equal to mu naught. And H sub A is that mu is less than mu naught. We can see that H sub A is going to be different in a second. Mu naught here represents the value that the claim says the population mean is actually equal to. So in this example, this would be the manufacturer's claim. So the alternate hypothesis can be less than, greater than, or just not equal to. So we could have mu is greater than mu naught, and mu is not equal to mu naught as well as alternate hypotheses. My null and alternate hypotheses for this example are H naught is mu is equal to 500 days, because the manufacturer says that the mean life of a battery is 500 days. And my alternate hypothesis is that mu is less than 500 days because you believe that the mean life of a battery is less than 500 days. A hypothesis is just a sentence with a name. So here we have the name of the hypothesis, for example, H naught. We have the subject is mu, the verb is equal to in this case, and the object is, in this example, mu naught. Now, how do we determine if the mean is less than 500? If we had calculated a sample mean of 235, then we'd probably say that this is a slam dunk, that obviously the mean life of an XJ35 battery is less than 500 days. If we had a sample mean of something like 435, you'd probably believe that the mean life of a battery was less than 500 days. But what about something like 483 or 498? At this point, we're getting into the territory of this might have just been chance. We might have just, gotten a few batteries that happen to have shorter than average battery life in our sample. Just by pure chance. And so the question is, where's the line? How do we find it? And the answer to that is we have to look at our sampling distribution. If the mean really was 500, what different sample means would we get if we did repeated random samples of 30? Well, sometimes we'd get more, sometimes we'd get less. And so we need to look at the distribution, the shape, the center, and the spread. The shape of our distribution should be normal. The center, or mean, of our samples would be 500 in this case. And the spread, or standard deviation of our samples, would be the standard deviation that the manufacturer told us, that's sigma, that's 25, divided by the square root of the sample size, which is the square root of 30. And a picture is always helpful here. This filled area represents the probability of getting a sample mean that small. So we see this is pretty small from the picture. And this is where we use a z-score to help us. Remember, z is x bar minus mu naught divided by sigma divided by square root of n. Our x bar is 490. Mu naught was the manufacturer's claimed mean battery life of 500. Sigma was the manufacturer's claimed standard deviation of 25, and 30 was our sample size. And using this formula is from chapter 6. We get that z is about negative 2.19. And this is a bit more than 2 standard deviations away from the mean, which is pretty far. We should look at the probability here as well. And to find the probability, we use this normal CDF function in our calculator, or the equivalent that you can find online. And we should get that the probability is about 0.0142. This means that there is a 1.42% chance that you could find a sample mean less than 490 when the population mean is 500 days. This is really small. So the chances are that the assumption that the population mean is 500 days is wrong, and you can reject the manufacturer's claim. But the question is, how small is small? How do we quantify small? Is 5% or 10% or 15% really small? How do we decide? Well, we need a couple more definitions in order to answer this question. The test statistic is this z value, which is x bar minus mu naught over sigma divided by square root of n, since this is calculated as part of the testing of the hypothesis. We also need this definition of what's called a p-value. This is the probability that the test statistic will take on more extreme values than the observed test statistic, given that the null hypothesis is true. It's the probability that we calculated above. We calculated a p-value. Now, how small is small enough? To answer this, we want to know about the types of errors that we can make. And there are only really 2 types of errors. There is the first type of error is when we say that H naught is false, when in fact it is true. This means that we reject H naught when H naught was in fact true. The second error is if you say that H naught is true when in fact it is false. This means that you fail to reject the null hypothesis when the null hypothesis is false. And we have a table here that categorizes this for you. So a type 1 error is rejecting the null hypothesis when the null hypothesis is in fact true. And a type 2 error is failing to reject the null hypothesis when the alternate hypothesis is true. And we have an observation here. There are two types of errors that are a type 1 error or false positive. This is believing that a pattern is real when it is not. And there is a type 2 error or a false negative. This is believing that a pattern is this is not believing that a pattern is real when in fact it is. If you believe that the rustle in the grass is a dangerous predator when it's just the wind, you are more likely to survive than if you believe that the rustle in the grass is just the wind when in fact it's a dangerous predator. Because the cost of making a type 1 error in this case is less than the cost of making a type 2 error, and because there's no time for careful deliberation between patternicities in the split-second world of predator-prey interactions, natural selection would have favored those animals most likely to assume that all patterns are real. So there are going to be cases when it's worse to make one of these errors. In this example, it's much worse to make a type 2 error to assume that the rustle in the grass is just the wind when in fact it is a dangerous predator. But there are going to be cases when making a type 1 error is more dangerous or costly or in general worse than making a type 2 error. And this is kind of what goes into deciding how small is small in terms of a p-value. So alpha is the probability of a type 1 error. And this is the probability that we reject the null hypothesis when the null hypothesis is true. Right? We're just phrasing this in a different way. Alpha is called the level of significance. We can design our testing to use alpha as our threshold. There's only one H in threshold. Beta is the probability of a type 2 error. This is the probability that we fail to reject the null hypothesis when the null hypothesis is false. This is also called there is a related concept called the power. Power is 1 minus beta. For a certain sample size n, if alpha increases, beta decreases. For a certain level of significance alpha, if the sample size increases, beta decreases. So alpha and beta are related, but they're not complements of each other. Alpha is usually chosen. There are only 3 values that are usually picked for alpha. Most commonly, we pick alpha equals 0.01, 0.05, or 0.10. Beta is actually much more difficult to find, so we usually don't find it. If you want to make sure that your beta, that your type 2 error is small, the best way of doing this is to just take as large of a sample as you can, provided that it's a representative sample. This is one use of power. We want for beta to be small and for the power of the test to be large. And the level of evidence depends on the crime in this case. If a type 1 error is really, really bad, then we want our alpha to be as small as possible. So we would pick something like alpha is 0.01. If a type 2 error is really bad, then we want beta to be as small as possible. And remember that whenever alpha increases, beta decreases. We want for alpha to be a little bit larger. So we would choose alpha equals 0.10 in this case. If neither type of error is bad, or if both are equally bad, then we would pick alpha equals 0.05. The main thing is we always have to pick the alpha before you collect the data and start the test. You can't collect the data, perform the test, see your p-value, and then choose your alpha. That is an incorrect way of going through this process. And that's actually led to a large number of problems in terms of statistics in the past in various fields such as psychology. So again, we have to choose this alpha before we collect the data and start the test. We cannot choose the alpha to fit whatever p-value we get. So now if we revisit this example, in this case, we state the random variable and the parameter in words. Here, x is the life of a battery, mu is the mean life of a battery. We state the null and alternative hypotheses and our level of significance. Here, h naught is that mu is equal to 500 days, and h sub a is that mu is less than 500 days. In order to determine our alpha here, we have to think about the consequences of each type of error. So in this case, you are a buyer who's trying to get out of a contract to buy these batteries. If you make a type 1 error, then we are saying that then you are potentially saying that the batteries are bad when they aren't. And in this case, the manufacturer will likely sue you, and you want to avoid this. So you might pick alpha to be 0.01 to make a small chance of making a type 1 error. Of course, this actually means that you have a larger chance of making a type 2 error. But what if the batteries are used in pacemakers, and you tell this person that their pacemaker's batteries are good for 500 days when they actually last less? In this case, if you make a type 2 error, you might end up killing someone. And it's probably better to be sued than to kill someone. So, in this case, you might want to pick alpha as 0.10. So in this case, because we want to avoid anyone dying as a result of our advice, we're going to choose alpha equals 0.10. We want to state and check the assumptions for a hypothesis test. We want to make sure that a random sample of size n is taken, that the population standard deviation sigma is known, and that the sample size is at least 30, or the population of the random variable is normally distributed, and these are all true. We want to find the sample statistic, the test statistic, and the p-value. Now, of course, we did the data collection actually before we stated what the alpha was in this case, but really, well, because we collected the data earlier, but in practice, again, we want to make sure that we don't collect the data until we have stated what our alpha should be. So we want to find the sample statistic and the test statistic. We've already done this. The p-value, we're using normal CDF. And the probability that we found here, that of the evidence that we saw, given that the null hypothesis is true was 0.0142. So our conclusion here is that because the p-value is less than 0.10, which is our chosen alpha, this is below our threshold of weirdness, basically. So we reject the null hypothesis. This means that the battery life was probably less than 500. In general, we reject the null hypothesis if the p-value is less than alpha, and we fail to reject the null hypothesis if the p-value is greater than or equal to alpha. The interpretation here is that, well, we are rejecting the null hypothesis, so we are tentatively accepting the alternate hypothesis. So tentatively, these batteries last less than 500 days. Or we believe that there is enough evidence to show that the mean life of a battery is less than 500 days. Now, this is statistically significant, but is it practically significant? Like, if you are the purchaser of these batteries, if you're contracted to purchase these batteries, would it be worth it to try to cancel your contract over this 10-day difference, right? In reality, for instance, if the batteries are used to replace in pacemakers, you would probably just tell the patient to have the batteries replaced every year. This way, you have a large buffer, whether the batteries last 490 days or 500 days. It might not seem worth it to break this contract over 10 days, right? Because you also have things like you might have a business relationship with this manufacturer that you don't want to destroy by breaking this contract. So even though sometimes things might be statistically significant, they may not be practically significant. The hypothesis test is just one part of a research process. There are other pieces that we also need to consider. And here we have a summary of this process. We state the random variable and the parameter in words, state the null and alternative hypotheses and the level of significance, state and check the assumptions of the hypothesis test, find the sample statistic, the test statistic, and p-value. Then we make our conclusion where we either reject H0, the null hypothesis, in favor of the alternative hypothesis, or we fail to reject the null hypothesis. You never accept the null hypothesis. You don't accept the null hypothesis ever. We do not accept the null hypothesis. If you wanted to accept the null hypothesis, then why even do the test in the first place? You wouldn't want to go through all the work and then just find out that you wanted to accept the claim. So this doesn't mean if we fail to reject the null hypothesis, it doesn't mean that we have proved the null hypothesis. It just means that we haven't, that we don't have evidence, that we don't have enough evidence to support or to prove the alternative hypothesis at this time.